This video is the first lesson of my 10-part series on Euclid's Elements for the Modern Math Academy course called Introduction to Modern Mathematics Part 1. This is part of a 4-part course covering Euclid's Elements, Carl Friedrich Gauss's arithmetic investigations, naive set theory, and model theory. If you would like to gain access to the other 9 lectures on Euclid's Elements, please visit courses.modernmathacademy.com. Welcome to the first episode of Intro to Modern Math Part 1, Euclid's Elements. This is Lesson 1. I'd like to just start off by asking the question, why should we study Euclid's Elements? This is Lesson 1 from the Part 1 of a 4-part series called Intro to Modern Mathematics. And there's no way to begin math without understanding this particular book, Euclid's Elements. This is the second most published book of all time and has affected the way all mathematicians think, period. And so that itself is reason enough, but there's many different reasons why we should study this book. This is going to affect all of math throughout history and the way math is written and presented. So this is a really important topic to start with. Why study this book at all? We could just start reading more modern math textbooks, but there's something transformational about going through this text in its original content. I often compare this to listening to Beethoven played by himself, Beethoven, or on a child's 8-key piano. They're going to sound very different. And so I'm absolutely excited to share this textbook with everyone. But today, what we're going to talk about is why should we study this at all? So a little bit of context, 300 BC is around the time that this was written by Euclid of Alexandria. So Alexandria is in Egypt. This is a major hub of the empire that was set down by Alexander the Great. This was a port for all of the trading in the Mediterranean. And so they had lots and lots of contact with math and science that was going on around that time. The word elements, you should think of the elements, right? So the word the elements means first principles, that from which all else may be derived. The 4 elements in ancient thought were earth, air, water, and fire, and all matter was some constituent combination of these 4 elements. And so the whole point of this book is that from 5 basic axioms or postulates, as Euclid calls them, or to understand what this means, obviously true statements, we can derive all known mathematics. This is an original idea to Euclid's Elements. This takes all of the known math at the time. Euclid did not create all of the propositions in here. Many of the proofs can be traced back to Eudoxus and many other mathematicians like the Pythagoreans and the school of math surrounding Pythagoras. But what is unique about Euclid is his methodology. He takes all of these facts about shapes and magnitudes and is able to boil it down to 5 basic ideas and using logic and reason to derive all known mathematics after that point. So Euclid's Elements is unbelievably large. It is a 13-book volume. Most people will find volumes with just the first 6 books, but Euclid has a total of 13 books that he has on various topics. This is all the known math at the time in 300 BC. There are 465 mathematical propositions put through these 13 books. There are a total of 131 definitions. Euclid defines what a point, what a line, what a square is, etc. And he has 5 postulates or axioms and 5 laws of logic. As we will see, these 5 postulates are how to use a ruler and compass, and then 2 other very interesting postulates. But for the most part, the context of Euclid's geometry is using a ruler and compass to construct different objects, and then using facts about these very simple tools to derive true statements about the drawings you can make with the ruler and compass. There's already here we can see a reductionistic mindset that we're limiting ourselves to only using a ruler and compass. It's actually not a ruler, because a ruler has measurements on it. The proper term would be a straight edge, which has no measurements, although Euclid can provably use a ruler if he wishes. We'll talk about that as we get there. But I think it's helpful to look at this and to see Book 1 has 5 postulates, 5 common notions, and 48 propositions. And the rest of the books have no postulates and no common notions. But this contains all known math. It's quite the feat. This is why this book was the #1 math textbook for 2,000 years, more than 2,000 years. So this is, as I mentioned, the second most published book of all time. The most published book is the Bible. The most printed book, actually, is Mao's Red Book, but that's for another day to discuss the impact of that book. This book has been read by everyone who is educated. And so there are things in common culture which go back to Euclid. For instance, when someone says the whole is greater than the sum of its parts, this is a tongue-in-cheek kind of phrase that is contradicting what's actually in Euclid, because Euclid has an axiom that says the whole is equal to the sum of its parts. But when you hear this phrase, the whole is greater than the sum of its parts, what's trying to be conveyed by that is the idea that a bunch of people come together and something bigger than themselves is formed from it, right? But this is a reference to Euclid's Elements. Most people don't know this. Another very common phrase that you'll hear is, how do you square that circle? This references a Euclidean style problem, which is trying to construct a square that has the same amount of area as a fixed circle. It turns out that that's actually impossible, but no one knew that for 2,000 years. People spent 2,000 years trying to construct a square with the area of a given circle. And so when someone says, how do you square that circle? What they're trying to convey by this is usually that you have some kind of contradiction or some problem underlying what you're saying. You have 2 ideas that are not harmonious with one another. But these are just 2 examples of how Euclid has been impacting our intellectual culture. So I have many different reasons why we should read Euclid's Elements. First of all, Euclid's Elements teaches us how to think. Thinking is pretty important. Most people don't think because thinking is an exercise. Thinking is not just letting words fly through your head. Thinking is dissecting, breaking things apart, and creating new ideas from them, right? To say that thinking is just expressing your thoughts, I think it trivializes what thinking truly is. Thinking is a much higher order aspect of what it means to be a human being. And if you want to learn how to think, there's no better way to do that than to study from Euclid's Elements. And if you don't believe me, maybe you will believe Abraham Lincoln, who had something to say about this. Here's a quote from Abraham Lincoln himself. He said, quote, "In the course of my law reading, I constantly came upon the word demonstrate. I thought at first that I understood its meaning, but soon became satisfied that I did not. I said to myself, what do I do when I demonstrate more than when I reason or prove? How does demonstration differ from any other proof? I consulted Webster's dictionary. That told of certain proof, proof beyond the possibility of doubt, but I could form no idea what sort of proof that was. I thought a great many things were proved beyond a possibility of doubt without recourse to any such extraordinary process of reasoning as I understood demonstration to be. I consulted all the dictionaries and books of reference I could find, but with no better result. You might as well have defined blue to a blind man. I said at last, Lincoln, you can never make a lawyer if you do not understand what demonstrate means. And I left my situation in Springfield, went home to my father's house, and stayed there till I could give any propositions in the 6 books of Euclid at sight. I then found out what demonstrate means and went back to my law studies. So Abraham Lincoln actually walked around Congress with a copy of Euclid on his person. As we will see as we work through this text, every ending of Euclid's proposition says, as was to be demonstrated. Right? In the court of law, to demonstrate something is very difficult. You will sometimes gather eyewitnesses, which can be unreliable. You might look for some material evidence. But Abraham Lincoln is living in the time before cameras and all kinds of other forensic evidence that we could have now, right? To become a lawyer, you have to demonstrate something. And he knew at that time that the only way to really demonstrate something beyond a reasonable doubt was mathematically. And so this is what Abraham Lincoln had to say about Euclid. Obviously, it taught him how to think. If you want to become a lawyer like Lincoln, then the number one thing you should do is read this book. This book will teach you how to think and how to make sure that the conclusions you draw are necessary from your assumptions, and that you'll know that what you have proven has been proven, right? How do you know that you've proven what you said you were going to prove? Well, by working through this textbook, you'll figure out what that actually means. And then you can use that as a standard. A very fascinating thing that I learned in a philosophy and history of math class that I took was about the medieval universities. So Aristotle's texts were rediscovered by the West, and they wanted to redefine the university to mean a place of science. And so there was actually a debate to get rid of mathematics from the curriculum because math was not science according to Aristotle. Aristotle wrote a book on literally everything. He kind of invented science per se. And science, according to Aristotle, was that which requires more than pure deduction. You need to actually reference some physical event in space and time in order for this to be science. And mathematics does use the physical world. We look at shapes to guess at our conclusions, but mathematics itself, as we'll see in Euclid, Euclid never says, and this one time I drew a picture of a triangle and it looked a certain way. Everything in mathematics is purely deductive. There's no reference to intuition. I mean, when we get into the text, we'll see that obviously it does guide our intuition. You know, Euclid is a first try at absolute deductive rigor. And the people in the 20th and 19th centuries who tried to do this ran into a lot of important problems as well. But we should understand, though, that even though they tried to get rid of math from the curriculum, everyone still learns math. And the reason is because mathematics trains the mind to do science. And so we kept math in universities because it teaches you how to think and how to do science. Science was the highest value of knowledge. According to Aristotle, math was the lowest. Many people have that pyramid facing a different direction now. We sometimes think that math is the highest form of knowledge. Definitely mathematicians think that. But math trains us to think. And I hope that these two examples of Abraham Lincoln and the medieval universities help make this clear. The second most important reason to learn about Euclid's Elements is that you cannot truly understand, quote, the West and its philosophical directions or trends without Euclid. I would argue that even postmodernism doesn't make any sense absent Euclid. Definitely the Enlightenment, the Renaissance, all of this was after Euclid was published in the Western world. It has shaped philosophy, it has shaped art, it has shaped everything. More importantly, what mathematicians discovered about Euclid in the 19th century led to postmodernism and the idea of relative truth, as we shall see. So, first of all, the West is a long arc of history. So, first of all, let's start very old with Plato's Academy. Plato was a world-famous philosopher in, not the entire globe of the earth, but all of the Mediterranean empires wanted to go study at Plato's Academy, which said, at the top, when you walk in, let none ignorant of geometry enter here. Plato's forms and ideas are one of the most impactful ideas, which is kind of circular. But all of this is in reference to mathematics and to Euclidean geometry. When you read the works of Plato, you will see Socrates make references to geometric shapes. And the Neoplatonic philosophers as well also were influenced by Euclid and read his works and commented on them and were inspired for their philosophical ideas, the idea of God as the one and the many forms of existence all necessarily protruding out from that. Euclid had a massive impact on the beginning of the West, which many would argue begins with Plato's Academy. But then throughout time, Euclid's Elements becomes the second most published book of all time. Literally all educated people read this, which would include the likes of René Descartes, who said, I think, therefore I am, the famous philosopher who gave us the Cartesian plane that everyone is forced to learn about in middle and high school. Galileo, Isaac Newton, Abraham Lincoln, Napoleon, Albert Einstein. Basically, every educated person read this book in school. It was mandatory. I have a somewhat provocative image here of the Grand Masons. You'll notice here a ruler and compass, and this is a reference to Euclid, who is often referred to as the geometer. He is held in such a high regard. Geometry itself is synonymous with Euclid. And so this is, again, just a very small list here. If you open Isaac Newton's famous textbook, which some would rank as high as Euclid's book itself, Isaac Newton's famous text Principia Mathematica, it literally just looks like Euclid. He quotes and cites Euclid's Elements in it as a major reference, but he's writing in that style. This is more than 1,000 years later. And Albert Einstein himself, as a young child, would study Euclid's work, and he would later actually develop ideas of physics that would contradict Euclid. So it's very difficult to fully explain how influential Euclid was to all of intellectual life. Moreover, not just intellectual life, but all mathematics and science has been held to the Euclid standard. Euclid didn't just write another textbook for the time. He wrote a textbook which changed the way every math textbook is written after it. All mathematics textbooks are written in Euclid's style: definition, theorem, proof, QED. Now, many textbooks will go through and write lots of extra commentary because the definition, theorem, proof style can be very dry and leaves no room for someone to do this by themselves. You really do need someone to walk you through this textbook because it doesn't explain itself. It just assumes you know what's going on. And that can be very difficult for self-study. But to this day, all math textbooks are definition, theorem, proof. If you aren't doing definition, theorem, proof, nobody would call that a math book. They would say it's literature or expository writing. Without definitions, theorems, and proofs, you're not doing math. And so that is how Euclid has impacted us. Science as well is written in this definition theorem proof. If you look at Isaac Newton's Principia Mathematica, it is written in this style. Even though you could argue he's doing physics or is he doing math, that's a conversation for a different time. But this style of writing itself has taken itself all the way into the 19th and 20th centuries. As I mentioned before, there were other people trying to do this. One example is Bertrand Russell, who wrote a book called Principia Mathematica as well. He spends 200 pages in this textbook trying to prove that 1 + 1 = 2 from first principles. This is exactly in the style of Euclid. Euclid is about shapes. Bertrand Russell's book is about sets and numbers, trying to be a little more primitive. But the methodology is the same. There was also this very famous group of 20th century mathematicians. It was a bunch of French mathematicians who got together and decided, we need a new Euclid. And they created a new name called Nikolai Bourbaki. Was a fake name that they wrote dozens of books under this fake name of Nikolai Bourbaki. And they rewrote all of mathematics based on set theory, much in the style of Euclid. They start with one single idea and use it to define and prove all known mathematical knowledge. This 20th century movement is exactly what Euclid did in his time. Another really interesting reference to Euclid would be the Declaration of Independence, which says, we hold these truths to be self-evident. That's saying that they're axioms. This is a reference to the Euclidean style of writing. The founding fathers of the American government wanted to start from self-evident truths and use these self-evident truths about man, nature, natural rights, and law to derive the American government from first principles. This first principles method is all Euclidean. Here are two random pages from Isaac Newton's Principia Mathematica, just to show you. So here we have proposition, and we have a little sketch drawing here, and we have some text, the labeling. If I didn't tell you that this was Euclid, if I didn't tell you that this was Newton, you would potentially think that this was Euclid. This is exactly what Euclid's text looked like. You'll notice here at the very start of the page, for the lengths which are not as number to number according to the 10th book of elements. Right here at the very top of this page, Euclid is being cited by Newton himself. And so this is in 1687. Another very important movement in the West was the idea that truth is relative. That is a very, very pernicious idea, which is affecting all of us psychologically. But what most people don't understand is that this goes back to Euclid. Euclid was eternal truth given by God. And the idea of contradicting Euclid was anathema. If you contradict Euclid, then everyone would just assume that you're insane. But in the 1800s, 3 different mathematicians in Germany, Hungary, and Russia independently discovered non-Euclidean geometries, whatever that means, we'll discuss. But this was not readily accepted. People were afraid to publish these results because they seemed to contradict Euclid. The mathematicians studying them tried to disprove these non-Euclidean geometries, but found it impossible. And so it took them a while to eventually posit that maybe they're just separate and different kinds of geometry. This has affected everything in philosophy. The idea that Euclid is not the only one truth, but we could choose which geometry to pick, has led to the idea of relative truth. An interesting reference to this is by Dostoevsky in The Brothers Karamazov. He has one of his characters say the following: if God really exists, and if he really has created the world, Then, as we all know, he created it in accordance with the Euclidean geometry. And he created the human mind with the conception of only the three dimensions of space. And yet, there have been, and there still are, mathematicians and philosophers, some of them indeed men of extraordinary genius, who doubt whether the whole universe, or, to put it more widely, all existence was created only according to Euclidean geometry. And they even dare to dream that two parallel lines which, according to Euclid, can never meet on Earth, may meet somewhere in infinity. I, my dear chap, have come to the conclusion that if I can't understand even that, then how can I be expected to understand about God? I humbly admit that I have no abilities for settling such questions. I have a Euclidean, an earthly mind, and so how can I be expected to solve problems which are not of this world? And so I accept God, and I accept him not only without reluctance, but what's more, I accept his divine wisdom and his purpose, which are completely beyond our comprehension. Anyway, you'd be surprised to learn, I think, that in the final result, I refuse to accept this world of God's, and though I know that it exists, I absolutely refuse to admit its existence. Let even the parallel lines meet, and let me see them meet. And I shall see and I shall say they've met, but I still won't accept it. So this character is coming to grips with non-Euclidean geometry and the absurdity of two parallel lines meeting. This is after 2,000 years of Euclidean geometry being held up as the standard of science and knowledge and math. And yet, people of the day, were thinking about these ideas, and it influenced Dostoevsky. So I think this is a very beautiful quote here. The third reason we should read Euclid's Elements is because mathematics has an aesthetic. Mathematics is beautiful and mysterious. There's something about math that it draws the feeling of egolessness, because it seems to be independent of humanity. And Euclid is one of the highest expressions of this because there's no commentary, there's no extra fluff. It's just definition, theorem, proof, definition, theorem, proof. There's some aesthetic there. And so I have a poem that I'd like to share. This is by Edna St. Vincent Millay. The title of this poem is Euclid Alone Has Looked on Beauty Bare. Euclid alone has looked on beauty bare. Let all who prate of beauty hold their peace, and lay them prone upon the earth and cease to ponder on themselves, the while they stare at nothing, intricately drawn nowhere. In shapes of shifting lineage, let geese gabble and hiss, but heroes seek release from dusty bondage into luminous air. O blinding hour, O holy, terrible day, when first the shaft into his vision shone of light anatomized. Euclid alone has looked on beauty bare. Fortunate they who, though once only, and then but far away, have heard her massive sandal set on stone. Here's another quote on the beauty of mathematics from Bertrand Russell, who puts it quite well. A very big influence Euclid had on Bertrand Russell to write a 200-page proof that 1 + 1 = 2. Bertrand Russell says, mathematics, rightly viewed, possesses not only truth, but supreme beauty, a beauty cold and austere, like that of a sculpture, without appeal to any part of our weaker nature, without the gorgeous trappings of painting or music, yet sublimely pure, and capable of a stern perfection, such as only the greatest art can show. One of the most beautiful and mysterious things in Euclid's Elements, which have been caught up in much spiritual practices, are these things called the Platonic solids. They are these 5 peculiar shapes which are made out of regular polygons. So the tetrahedron, the first one here, is made out of 4 perfect triangles. They have the same lengths and angles inside of this equilateral triangle. And using an equilateral triangle, we can construct a tetrahedron, or this third shape, the octahedron, or finally the icosahedron, can be constructed out of equilateral triangles. Similarly, with an equilateral square, we can construct a cube, and with an equilateral pentagon, we can construct the dodecahedron. The 13th book of Euclid is all about constructing these 5 shapes, but moreover proving that these are the only 5 such shapes made only of a single regular polygon. These have been studied extensively, but why 5? That's the question. That's the mystery. That's the beauty of what's happening here. As Paul Erdős says, if you don't understand the beauty of math, I can't really help you. He says, if you listen to Beethoven and you don't hear how beautiful it is, I don't know what else I can do to tell you. But these particular shapes have been caught up in all kinds of mystical practices like Kabbalah and many other different things, including astronomy. But the question is always, why these 5? And if you want to know why, well, Euclid has the answer for you. Another really interesting thing about math and aesthetics is that most notions of beauty are mathematical. When people analyze all the beautiful people and put their faces together in a computer algorithm and generate a single image, what they get is a perfectly symmetric face. Even beauty that breaks symmetry, right? When someone has a beauty mark on one side of their face, what makes it beautiful is it breaking the mathematical symmetry. There's no way to define an aesthetic that does not have something to do with mathematics. And so beauty itself is somehow tied up with math, whether we like it or not. The 4th reason why we should read Euclid's Elements is because The 4th reason why we should read Euclid's Elements is because studying mathematics makes us better people. It opens our minds, but also trains them to conform to rigorous logic. As I mentioned before, Euclid is, in some sense, eternal and incorrigible. You cannot contradict Euclid. It has been compared to the mind of God, or said to be the closest to the mind of God that man has achieved. It is the highest and purest form of thought. It is true now, it is true tomorrow, and in a sense, we think it was true before Euclid wrote it down. Right? So this is why it was such a shaky event when quote-unquote non-Euclidean geometries were discovered. So I would like to really hammer this home by explaining what is Euclidean geometry. When we say Euclidean geometry in the modern world, we mean the geometry you learn in high school. Most people learn this fact here, that all triangles have their angles summed to exactly 180 degrees. But what if they didn't? Right? Well, if you were to say that, then everyone would just say, well, you're insane. And they would probably tell you to go to sleep and wake up tomorrow and come back to the truth. But is this always true? As it turns out, it's not. So here are 2 very simple examples. The Earth is not Euclidean. So we can look at this example here. We start at the North Pole, at the top of the sphere, and walk down to the equator. When we're at the equator, we make a left and keep walking until we are 1/4 around the Earth. So 25%. When we get there, we walk north again until we land at the North Pole. And this has drawn a 3-sided figure on the Earth. Well, unfortunately for Euclid, all 3 of those angles are 90 degrees. And so this triangle does not have 180 degrees. Well, now obviously you'll tell me, well, but this isn't flat, right? Yeah, that's kind of the whole point. actually. Here is another example. This is called hyperbolic geometry. It looks kind of like a Pringle chip. Triangles on a hyperbolic shape will always have less than 180 degrees. And so these things are true, but they're absolutely confusing because we spend 2,000 years thinking that all triangles have 180 degrees as the sum of their angles. And yet, what is a triangle? It's a figure with 3 sides. These do have 3 sides, do they not? So how do you square that circle? Well, that is the story of the 20th century, is trying to square this circle. And this has shaped all of Western thought, period, has been impacted by this. But these notions are not actually that new. Non-Euclidean geometry has been explored in art. For instance, when everyone draws this famous one-point perspective when they practice for their art class, that is not Euclidean geometry. There are no parallel lines in projective geometry. All lines intersect at the point at infinity. In Byzantine art, there was a reverse perspective perspective geometry, where instead of things getting smaller as they move further away, they get larger. So the idea is that you are stationed at the point at infinity. M.C. Escher is a much more modern example of this. M.C. Escher is explicitly making hyperbolic geometry. So this shape here with the angels and demons, or angels and bats, this is what is called the Poincaré disk model of hyperbolic geometry. All of these angels are the same size. Now, as we see it, it looks like they get smaller and smaller, but that's because this is a model of hyperbolic geometry. We don't live in hyperbolic space. If we did, it would be very confusing. So these ideas of non-Euclidean geometry are all through art, but what really put this paradigm into tension was Albert Einstein's theory of general relativity, which we have now verified is physically the case. So the universe itself, in the presence of matter, is non-Euclidean. So I have here on the left, we have a kind of graphic representation of something that we see pictured here on the right. So this is called gravitational lensing. So as it turns out, the sun, or galaxies or stars, have mass, and this actually curves space so that it is not Euclidean anymore. And so what we're seeing here is that there's a large cluster in the middle between the Earth and this other faraway galaxy. And because that galaxy is so massive, it curves the space, which causes the galaxy behind to be presented to us in this weird ring or U shape. So this is a real observation. This can kind of give some context to the work of Pablo Picasso. Historically, it has not been demonstrated that Pablo Picasso himself was influenced by non-Euclidean geometry, but we do know that his friends were. So we can only connect the dots there. This image of a person here, this is a painting by Pablo Picasso, you can see that it is one side of their face, and yet we can see the eye on the other side. These ideas can be explored in reality, only hypothetically. When space is curved around a black hole, if you were to look sideways, you would actually see the back of your head, which is very confusing. But these ideas are absolutely radical, and they blow our minds wide open. I don't know if anyone really understands this, but the math checks out. We can write all this stuff down and it works. And then when we look with our telescopes, that's what it looks like, right? We cannot understand any of these mind-bending realities without first grappling with the origin, which is Euclid's Elements. So why should we read Euclid's Elements? Again, Euclid's Elements teaches you how to think. You cannot truly understand the West and its philosophical directions or trends, even postmodern, absent Euclid's influence. Third, because mathematics is beautiful and mysterious. And fourth, because studying mathematics makes us better people. It opens our minds, but also trains them to conform to rigorous logic. Logic can lead us places that can be confusing, like non-Euclidean geometry. But it shapes our minds nonetheless and makes us better people because of it. And so that will wrap up our first lesson here. Why should we study Euclid? My next lesson, I would like to talk about what is actually in Euclid. I showed you on the second or third slide the contents. We have 456 propositions, but what are they all about? So I'd like to now start studying Euclid. So remember, studying this initiates you into a rite of passage. This is something every educated person has done over the last 200 years. But before we do that, I'd like to warn you, a warning Euclid himself gave to King Ptolemy. There is no royal road to geometry. Or as I like to tell my students, we all must suffer to learn mathematics. So thank you very much, and I will see you in the next lesson. If you enjoy this content, make sure to like, share, comment, subscribe, and hit the bell for notifications. If you want to take your knowledge of math to the next level and/or join a community of math lovers, please head over to courses.modernmathacademy.com to become a member of the Academy and start learning today. From me, Dr. W.